In this video, we're going to see the step-by-step solution of the PKN model for a fluid-driven fracture. Here, the objective is not to see step-by-step the solution, but rather to understand how to solve these problems if, for example, you wanted to write your own fracture simulator, or if you wanted to relax some of the assumptions that we have in here and might require a numerical simulation. So the PKN solution, we're going to see that it can be derived very nicely analytically for some assumptions. And then if you wanted to relax some of these assumptions, you could do that by understanding which are the steps that you have to relax and that you may have to change. All right, so the PKN model is derived from the names of Perkins, Kern, and Nordgren that came up with this simplified model to predict the propagation of a fluid-driven fracture. The main assumption here is the geometry of the fracture. And in this case, we assume that the fracture has a constant height, something that we're going to see in a bit how to determine, and that the fracture has a width that varies along the fracture height. Let's assume this is a vertical fracture. So in direction Z, the fracture width varies. And that we can assume that we have a state of plane strain in the plane perpendicular to the long axis of the fracture. So for example here, a plane YZ. The plane YZ is, as we said before, is going to be the plane of plane strain, and we're going to see that that's going to make our life quite easy because it's going to allow us to obtain the analytical solutions of fracture deformation for this plane. There is a little thing to notice over here, and is that when we are assuming this plane strain in each successive plane YZ along direction X, we're disregarding a shear stress going from one plane to the other. So that's not mechanically rigorously correct, but for this model it works more or less well. But just keep in mind that we're trying to solve a three-dimensional mechanics problem with a simplified 2D model. This is actually a 2D model because the solution is just in the plane YZ, which is good enough. It's not perfect, but it's good enough. Okay, with the geometry tool, one of the main assumptions here is that the fracture half length is going to be higher than the fracture height. That's something required for the solution to work well. And we already talked about the plane strain. And some other thing which is going to be important is that we're going to disregard the fracture toughness of the rock. So we're not going to impose any criterion on fracture propagation. Basically, our toughness is going to be equal to 0. All right, so let's see how we solve this problem. Remember that this is a coupled problem involving fluid going through the fracture and opening the fracture, and that's causing the fracture to propagate and to grow in direction X. All right, the first thing that we're going to do is to determine the height. This is not really part of the PKN model, but just to close the discussion about fracture height, let's just talk briefly about that. Usually the way we will determine the fracture height is by analyzing the stresses in situ and looking at the variations of horizontal stress as a function of depth. So for this example, I have a tectonic strain, which is the same all over the different layers in a geological formation. And I happen to have a place in which I have a soft layer bound by two stiff layers. So if I apply this action, the tectonic strain, on this system, which is the one composed by the plane strain stiffness or plane strain modulus E prime, the result is going to be a horizontal stress that follows the profile of the stiffness. And therefore, here, if my net pressure in my fracture is smaller than the contrast that I have from layer to layer, the fracture is going to grow just in this section because it is going to prefer to stay within the region with lower net pressure. All right, so in this case then, let's say that I have a fracture that starts at this point, is going to grow, and is going to grow as a plane in the direction, in the plane YZ coming out from the screen, and it will grow, eventually find the bounds, which are the two stiff layers, as long as the net pressure in the fracture does not exceed this fracture barrier, or this, you may think in terms of chemical terms of inactivation energy. As long as it doesn't go above that, then the fracture will remain bound in this layer and will not go into the stiff layers. And that's why how we're going to determine our fracture height. Of course, you know, this is a very simplified version of the fracture height. Sometimes it goes a little bit beyond that, those strict bounds, even if it doesn't go into the stiff layers. But this is an approximation which is good enough for now. Remember that if the net pressure were to grow and exceed this threshold, then the fracture may go into other layers. Okay, now that we have the fracture height, we can continue. In the PKN model, remember that the fracture height is going to be constant, and we're going to assume that along the entire fracture, the fracture height is the same. All right. The next thing that we're going to do is we're going to solve for the fracture width. And in order to do that, we're going to use the Griffith solution. If you remember, the Griffith solution tells you what is the width of a fracture with a constant pressure. And this solution is actually very, it solves very well our problem that we have over here, because we know that the pressure varies along the fracture. But if we take a given plane, what we're assuming right now is that the pressure in this plane is the same. That the pressure here is the same as there, and is the same as here, in the same plane YZ. We know that as we move in X, the pressure is going to vary, but at the given X, the pressure is going to be all the same in this plane. And that's what we're going to do, and how we're going to use the Griffith solution. The Griffith solution depends on a fracture half length. And that fracture half length, C, in this case, is going to be the fracture height divided by 2. So I can go ahead into this equation now and write that this is going to be equal to C is going to be the fracture half length divided by 2. So when I do that 1 over 2 factor times 4 is just going to be 2. So this is going to be 2 times the net pressure as a function of x, which is a variable as a function of x, times the fracture height divided the plane strain modulus. And this is going to be the width of the fracture along direction x, which is a variable. All right. Now that we know what is the fracture width, we can go ahead and solve for the flow within the fracture. For the flow within the fracture, we're going to assume that we are dealing with laminar flow, and that we have a Newtonian fluid, and therefore we can find a solution for that equation. Probably you are familiar with the solution of fluid flow between two parallel plates. And this solution is very similar, but instead of fluid flow between two parallel plates, now we have a fluid flow through an elliptical channel of constant width. For that solution, we can still apply because we're just calculating the gradient of the pressure at a given width. We know the width is going to vary, and so will the pressure gradient as a function of that. But since we're calculating just the gradient, this is enough for now. So in this equation, we have the pressure gradient along the fracture, along direction x, and we see this is a function of the viscosity of the fluid, the rate of fluid flow through the fracture, the width of the fracture, and also the fracture height. All right, now that we have the pressure gradient along the fracture, we can add one more equation, and this is going to be mass conservation or material balance. In this case, what we want to do is we want to account for the fluid that goes in the fracture and the fluid that gets lost into the formation in the form of leak-off. The amount of injected fluid, we can divide it in two, into the volume that stays in the fracture and keeps the fracture open. Remember that in order to maintain material balance and to keep the fracture open, you need something in there, and that something is going to be the fracturing fluid. So the injected fluid is going to go into the fracture to fill the fracture, and some of that is going to go into the formation in the form of leak-off. If you wanted to solve for leak-off, you have two approaches. You could either go this route and assume a simplified solution with the Carter leak-off coefficient and assume that the leak-off depends on a square root of time. This is a typical solution for fluid flow from a planar fracture. Or if you want a rigorous solution, then you just apply Darcy's equation and the material balance, and you just solve for fluid flow in a porous system, in a porous medium. You could go either way. In this case, we are going to assume that the leak-off is going to be equal to 0, just to make our life easier. So this is one of the points in which we start to work towards a solution which is simpler to deal with and to obtain a solution, but this is something that you could relax if you wanted to write, for example, a numerical solution for this same problem. Since I'm talking about this, let me tell you also that you could relax this equation too. If you have a non-Newtonian fluid, then this solution is going to be different. You could relax also this part and this equation. You may have a fracture height that varies with length, and that's going to be a little bit more difficult to handle, but you could do that. Eventually you could do that, and that's what hydraulic fracture simulators do. All right, so let's come back over here. Assuming that the leak-off is going to be equal to 0, then I can write what is the injected volume as a function of time. I'm going to further assume that the injection rate is constant. So this is another thing I'm doing in order to make the solution easier. If the injection rate is constant, then the volume of injected fluid is going to be equal just to the injection rate times the time, because this one is a constant. And all the fluid that goes through the fracture is going to be equal to just the injected fluid. One clarification, the injection rate I just refers to one wing. So we are just obtaining the solution for the fracture half length, and therefore we're just using injection rate for one wing. All right, let's see what we do with that right now. Basically, we have all the equations that we needed, and now we just need to look for the solution. And we have assumed a few things that are going to make this solution easier to obtain analytically. All right, let's put together equations 1, 2, and 5. Equation 1 is the equation of the width. from Griffith. Equation 2 is the equation of pressure gradient from just fluid mechanics. And equation 5 is just saying that the flow rate is going to be what I inject in the wellbore divided by 2, because it's just one wing. All right, then from equation 2, the width is what I have from Griffith, which is right here. And also replacing Q by I, this is the equation I get. So Q now is I instead of the width. Now I have the solution from Griffith. And this equation tells me that the pressure gradient along the fracture is going to be a function of all these parameters. Some of them are constant, some others are not. Particularly the net pressure along the direction X is not a constant. All right, so I can simplify that. Notice that this one is 64. We have a 64 over here, and we have 2 to the third, which is 8. So 64 divided by 8 is going to be 8. And what else? We have a pi. The pi survives. We have a plane strain modulus here, which is dividing. So it goes multiplying on the numerator. The net pressure goes to the cube. And the fracture height, we have here a power of 3 plus 1. That's going to be power of 4. So it's the same equation. The next thing we're going to do is, in order to solve this equation, now this is just a derivative, it's a gradient. In order to solve this simple differential equation, we're going to integrate the equation, going from the position x equal to 0 where the fracture starts to the tip of the fracture, which is the position xf. So here I have my variable that I'm going to integrate, the variable dp, and what I'm doing is I'm integrating by parts. See, this one, the net pressure goes over here, and the dx, which is for the length, goes over there. So I just separate my variables, and I'm going to integrate Pn from Pn at position 0 to Pn at position x, and this other part of the equation, which the variable is x, from position 0 also to position xf. And this is just a simple integral. This is the integral of a polynomial. So the solution is going to be that function to the fourth power divided by 4. And here these are the two bounds. So this is going to be the net pressure at the tip to the power of 4 divided by 4 minus the net pressure at the beginning of the fracture, or at the wellbore, to the power of 4 divided by 4. And on this side, I have all of these is a constant: viscosity, injection rate, Young modulus, plane strain modulus, actually, pi, and the fracture height. This is all a constant, so I can take it out, the integral, and the only integral I have here is just the integral of 1, and that is just x. So this is going to be xf minus x at 0, which is equal to 0. All right, now that we have done the integral, we're very close to the solution for this problem. I'm going to do one more thing over here, which is going to be to assume that the net pressure at the tip of the fracture is equal to 0. And that assumes that basically you don't have any pressure at the tip in excess of the least principal stress. And it's an assumption that makes sense. Sometimes it may not be strictly true, but it makes sense, and it makes sense, of course, that the pressure is the highest at the wellbore, and then it decreases as you go to the tip. Well, in this case, to make everything easier, we're just going to assume that this one is equal to 0. And of course, 0 is equal to 0 too, so we can get it out of the equation. And what we're going to get now is the equation of the net pressure as a function of the fracture half length. So notice that here we have a 4 times 8, that's going to be 32. And this power of 4, I'm moving it to the other side. And now I have everything to the power of 1 over 4. So I'm just rewriting this equation over here. But good news, now we have a solution of the net pressure at the wellbore, position x equal to 0, as a function of the fracture half length. And I can work with this same equation and combine it with equation 1, which is the equation of the Griffith solution for the width of the fracture, as a function of the net pressure. And I can obtain also at the coordinate x equal to 0 what is the width of the fracture as a function of the fracture half length. All right, so what do I do now? I have these static solutions, but I would like to have my solution as a function of time. So in order to put time into the picture, what I'm going to use is the equations of material balance. And what we're going to do here is to recognize that the volume of the fracture is going to be a function of the fluid which is within the fracture. On one side, the volume of the fracture can be written as the fracture half length times the fracture height times the average width, right? So this is a volume, so we're multiplying three quantities, where the average width gives us the volume when we multiply times these other two. This is just a geometry problem, and you can show that the solution for this is that average width is going to be a function of the width at the coordinate x equal to 0 times pi over 5. And on the other hand, we are going to assume in this case that since we do not have leak off, all the fluid that we injected is actually filling the fracture, and that's going to be the injection rate times the time. Where the injection rate, of course, is a volume rate, right? So volume divided by time times time, that's going to be a volume. So I can put this together, and I can also find an equation of the fracture half length as a function of time. And finally, the only thing I'm going to do is to combine equation 7 and equation 8, and I can obtain the final equations of the PKN model of the fracture half length and the width as a function of time. And also, if you add to that equation number 6, which was the equation for net pressure as a function of fracture half length, now since we have fracture half length as a function of time, we can plug that in there, and that will give us a solution of the net pressure as a function of time at the wellbore, or at the beginning of the fracture. And there are a few things to notice in this solution. Here, I'm just skipping these steps, but it's just algebra, how to get from the previous equations that we had to these equations. Just a lot of powers and moving things around, but other than that, it's not too difficult. So I'm just saving time here and just giving you the solution. Okay. Something very important to notice about this solution is that how the fracture half length varies as a function of time and the width and the net pressure. And you can see that because of this power of 4 over 5, if you were to plot this result, you would obtain that as a function of time, the fracture half length is going to grow and increase, and that makes a lot of sense as a function of time. So the longer the time, or the higher the time, or the more you go in time, the longer is going to be the fracture half length. That makes sense. But let's see the other ones that are less intuitive. Will fracture width increase with time too? Yes, it will. but notice that it's not going to increase as proportional as the fracture length does. Actually, the fracture width of the wellbore is going to look a little bit more like this, where it's going to tend, at the beginning it's going to increase quickly, but after some time it's not going to increase that quickly anymore because it's to the power of 1 over 5. And the last one, the net pressure is going to also increase as a function of time, and similar to the width, is going to increase quickly at the beginning, but then it's going to tend into smaller and smaller increases. And that's kind of expected because of the width is not increasing that much. And remember that in order to keep the fracture open, we need a net pressure to do that. But if the width required to do that is not that much, then the net pressure is not going to be that much either. So this PKN solution for this simplified problem is just an example of how you can solve these problems of fluid-driven fractures. And this solution is a good example because we can obtain an analytical derivation of the solution. You can do something similar for other models and other simplified geometries. For example, here I have two other models, which are called the KGD model and the radial or penny fracture model, in which we can assume the plane strain plane in different directions, and that will give you different solution. So for example, for PKN, we saw that the plane strain was assumed on a plane which is perpendicular to the direction of the fracture, the longest direction of the fracture, this plane over here. In the KGD model, the plane of strain is the plane that goes along the fracture length. And for example, here the width of the fracture is assumed constant as a function of depth for a vertical fracture. And this will give you another solution. And also we have the model of the radial fracture, in which we have a axisymmetric geometry in the plane which is the plane contained by the axis of this radial fracture. So either this plane over here or that plane is the same because they are symmetric along the axis that is going in this direction, connecting this point and that point along the axis of this radial fracture. Let me do a schematic of that because I think what I'm saying is kind of difficult to understand. So if we were to assume this fracture in 3 dimensions, this radial fracture is going to look like this, and the axis of symmetry I'm referring to is this one. So either this plane or that plane or any plane that contains this direction is going to be the same. So these analytical solutions then they give us an analytical answer of the problem. And here, if you want to see the solution of those, we're not going to solve them in detail. And here I'm going to post this link in which you can see not only the PKN solution, here's the PKN, but also the KGD solution, and I'm missing, I should put the radial solution too. Probably I will upload that soon. And that you can use these equations directly from there. Okay, and just coming back to this, there was one more thing I wanted to say, and this is that remember that these analytical solutions are useful just to get started in understanding this problem, and to serve as a base to solve more complex problems where we relax some of the assumptions that we have done so far. We're going to see that some of these solutions are also very useful for understanding some other problems and for treating analytically some of the solutions and, for example, seeing where the energy of the fluid is going, whether it's going into moving the fluid along the fracture or opening the fracture or creating more surface when a fracture propagates. So do not underestimate the power of these analytical solutions. They are useful to get started to build more complex models, and they are also useful to understand the physics of fluid-driven fractures.